Log on, tune in, find out. Another good idea from Cambridge.
Welcome you to the second lecture of this afternoon. Bertram Düring, who recently joined the University of, actually the mathematics department of the University of Sussex, and in the beautiful city of Brighton. And Bertram is going to speak to us on the gradient flow scheme for nonlinear fourth-order equations.
Yeah, well, thank you for the introduction and thank you for having me here. So first I must apologize that my talk will not be strictly kinetic, so as you can maybe guess from the title, but I thought it would be interesting also for some of you in the audience to hear something about our recent work together with my co-workers Daniel Mattes, who's now in Munich, and Peter Milicic in Zagreb. Okay, so nonlinear diffusion equations of fourth and even higher order have become increasingly important in pure and applied mathematics. You all know the well-known examples like Cahn-Hilliard equation, lubrication equations, fluid-type quantum models for semiconductors. And apart from their interest in applications, in theoretical physics, in engineering, they also spur a lot of interest because of their mathematical analysis, which is much more challenging because their behavior is typically much richer than that of the well-studied second-order equations. And so many questions until now still remain open. In my talk, I will concentrate on a particular equation. It's the fourth-order Derrida-Leibowitz-Speer-Spohn equation. It's a parabolic equation for the unknown function u. You have here these four derivatives.
I guess there are two R in Derrida.
There's so? Ah, sorry. Oops. Okay. So I should change that when we put it on the web, right? Okay, so I've written this here only in one space dimension. And originally it was derived for spin systems. So they wanted to model spins which interact, and in a thermodynamical limit, they derived a random quantity u that is related to the interface between these positively and negatively spins. And this quantity is governed by this equation. Another application where this equation arises is for charge transport in semiconductors. There u is the electron density. So for example, if you consider a simplified quantum drift diffusion model like this here, T is the temperature, U is the electron density, and V is the electric potential that consists of two parts. One is the classical potential and the other is the Bohmian potential, which is considered to model quantum effects. Then somehow in a strange limit of zero temperature and no classical potential, you would receive this equation. So there you end up with types of this equation from different applications. And I will not speak so much about the analysis, but just to revisit some of the results to make sure that we have solutions. Clearly the challenges are that we have a strong nonlinearity, may become singular for u equals 0. We have no maximum principle for these fourth-order equations. So Bleyer-Leibowitz-Speer proved using semigroup theory some local classical solutions exist in 1D. Then there's a paper by Jüngel and Pinnau who proved that global non-negative weak solutions in 1D may exist. And recently a paper on the proof that global weak solutions in RD exist by Jüngel and Mattes if the initial conditions have finite entropy. And there are also other results available, so the analysis of this equation is now quite good understood. How about numerics? So numerical difficulties, of course, are these fourth-order derivatives, strong nonlinearity. You should try to preserve the non-negativity of the numerical solution. And what people tried are mainly finite difference schemes. So maybe the most reasonable approach that you would think leads to good results, but is computationally expensive, would be to use a fully implicit finite difference scheme. Then you can now try to rewrite the fourth order equation as a system of second order equations with some flux f and solve that by implicit Euler. In a reformulation of the equation, Carrillo together with Jüngel and Tang solve that using a semi-implicit method. So there are some approaches to solve that numerically as well. But the equation also has another important property that I didn't mention yet. It constitutes a L2 Wasserstein gradient flow of the Fisher information, which is given here. So I think this was first explored by Giannazza Savary and Toscani. And this gradient flow information is quite useful from an analytic point of view. It allows you to give a geometric interpretation of the dynamics and paves you the way for analytic proofs, equilibration, to steady states and things. And it also gives rise to a natural semi-discretization in time of the evolution, the so-called minimizing movement scheme. And this is the key idea that is behind our scheme. So I will shortly introduce you with this minimizing movement scheme. And to do that, let's consider a simple situation now in finite dimensional space, Rd. So consider such a finite dimensional gradient flow for x of t in Rd, such a smooth potential phi. And then if you discretize this by the following scheme with this time step tau larger than 0, that is the solution at the new time step you obtain as the minimizer of such a functional that consists of two parts, of the potential and also of such a fidelity term. So you don't want to get too far away from the solution of your previous time step. Then if you consider the critical points that the minimizer of this optimization problem should satisfy, and if you write that down, this critical condition, you regain nothing but an implicit Euler step for this equation. So this is well known. And you can do something similar for the DSSS equation, and then this turns into the following scheme, that the solution at the new time you obtain as the minimizer of some functional, which here now consists of a part which consists of the Wasserstein distance between the new solution and the solution at the previous time step and the Fisher information. And our goal is now to derive a practical method from this minimizing movement scheme. For simplicity, we consider this only in 1D as periodic boundary conditions. And due to some technical reasons, we also will only consider symmetric densities which satisfy this property. Somewhere in many papers which study the numerical solution, also the densities are symmetric, so it could also be removed, but it would make everything much more technical. So we will stick with this assumption. So to solve now this optimization problem, there are two general directions. So, because of course we were not the first to think of you turning that into a scheme. However, our approach, I think, is first for a fourth order equation, and also it's quite different from the existing ones. One idea would be to optimize first and then discretize. That means you derive the Euler-Lagrange equations for the optimization problem and then discretize that with the numerical scheme. So, for example, in the paper of Carrillo and Moll, this was done. And our approach would be to discretize first, that we want to replace the continuous optimization problem by a discrete one, and then perform the minimization of a suitable finite dimensional subset. So before I will introduce the spatial discretization, I want to rewrite this function in a more explicit manner using the so-called Lagrangian coordinates, because this will allow us to compute the Wasserstein distance between u and this u star more efficiently. So how can you compute that more efficiently? If you have two measures and you can define their distribution functions denoted by capital U, then these capital U's are right continuous and monotonically increasing. That means they possess right continuous increasing pseudo-inverse functions defined in that way. And then you can, in 1D, very easily compute the Wasserstein distance by evaluating this this norm of these pseudo-inverse functions. And we will refer to this u of x, we call it omega, as the Lagrangian coordinates in contrast to x, which is the Eulerian coordinates. So we want to use this easy formula for the Wasserstein distance. This means we have to transform everything to the new coordinates, also the Fisher information. And okay, this is not just some calculations that I skipped, but you can rewrite the Fisher information in the new coordinates. Then the derivative of this pseudo-inverse appears, so we introduce this as our new unknown, small g, and we can write the Fisher information in that way. And since we want to stick now with this new unknown, we have also to rewrite the Wasserstein distance in terms of small g, which after some computations you end up with such an integral. It looks now a little bit more complicated, but we will see that we can later evaluate this integral quite easily in our scheme. So we have come from the minimizing movement scheme, and we have transformed everything to these Lagrangian coordinates. So let's summarize what we have. Our solution at the new time step is obtained by minimizing this new functional psi, and we have to, of course, to transform the initial conditions as well. And then we minimize this functional, which consists of the Wasserstein part, written in this new unknown function, and the Fisher information. And we have to do that for all functions which act on this space from 0 to mass m. So you must remember we have switched to the Lagrangian coordinates. We're not on the interval 0, 1 anymore, but from 0 to mass m. And also we have to satisfy this mass constraint. So if I sum up all the mass, then I get the whole interval of length 1. Also, can be seen that these functional values of the original and the transformed, they just coincide. And when we have, by our numerical method, found out some gn, we can recover the un, which we are interested in, by this reconstruction formula. Yeah? So now to the spatial discretization. We are now working in this space of these small omegas. So we choose a mesh with n+1 points. Starting point should be 0, the endpoint in large M, which is the mass, which satisfy also the symmetry property that we spoke before. And let's introduce some notation for the gaps in this mesh. So this mesh is not equidistant. We introduce small deltas as the gap between adjacent omegas and these large deltas in this way. And now we consider not all functions g, but we want to reduce our problem to a finite dimensional subproblem, and we consider only functions g that are in ansatz space with which is made out of basis functions phi k, and these are simply head functions on these omega, like in Galerkin approach, and you have weights gk. Yeah? So we want to look for functions in this ansatz space which minimize the functional. So then we can try to write all our continuous optimization problem in Lagrangian coordinates in a discretized version. So we have to find explicit representations of our new functional psi in terms of the weights and the parameters that appear in these head functions. And this can be done. And you can see that the Wasserstein part is just a quadratic form in these weights of the weight vector g with some coefficients, ajk, and these are coefficients of a symmetric positive definite matrix. You can compute also this matrix. It looks a little bit maybe complicated, but you don't care because only the computer has to remember you. So you can compute all these integrals over the head functions. And then you have the Wasserstein part. You need to discretize the Fisher information. If you have a function g in this ansatz space where you have a weight vector bold g with gk and so on inside, then in such an interval you can write the function in this way, just because it consists of the two head functions that live on this interval. And then you can use the representation of the Fisher information that we have seen before in the Lagrangian coordinates by such a discrete formula. And okay, then you can just insert this here, and you end up again with a discrete version of the Fisher information, which only uses the weights gk and these deltas here, which are the gaps in the mesh. So we have now discretized everything. We have gone over from the original formulation of the optimization problem to the Lagrangian formulation and over to the fully discrete one. But the minimizer is still subject to the mass constraint. We don't only have to minimize the functional, but also the solutions at the new time step have to fulfill the mass constraint. So let's introduce a Lagrange multiplier and the Lagrangian functional associated to this optimization problem. So it consists of the part, the discretized functional psi, and this constraint here. Then we are looking for solutions, and these are critical points of the Lagrangian satisfying this necessary optimality condition, where this bold G is given by the GK that you obtain by the partial derivatives of the Lagrangian, and for the last partial derivative with respect to the Lagrange multiplier, you recover the constraint, of course. And now it's a good idea to apply Newton's method to this first order optimality condition. And this leads us to our complete discretized algorithm that consists now of two loops: an outer loop where we do the time stepping, and an inner loop where we have to solve this Newton system. So given a solution at time step n, we define new starting iterates and then iteratively make Newton steps. So here you have this G from the first order necessary condition. Here you have the Hessian of the problem. And we iterate until certain stopping criteria are fulfilled. And then you can define the solution at the new time step n+1 as the final iterates from the inner loop. And then you continue in the outer loop until you reach the final time that you want to have. Okay, I want to show you also some numerical results now for this Wasserstein gradient flow scheme. Here on a grid with 100 grid points, we use the following initial condition with a small parameter epsilon, 10 to the power -3, and here the cosine with some exponent. On the left we have the exponent with m = 1, on the right hand side with m = 8. So here we have the recovered, the quantity of interest, the solution u over the space interval x, and the bold line in both cases is the initial condition. And here on the left hand side you see that there's one minimum, and then the solution relaxes very fast on a very small time scale to the constant steady state. The right picture is a little bit more interesting, because here you see that you start with this solution, then you have two minima developing, and then they finally merge into one minimum. So, and then it starts approaching very fast the constant steady state. And another thing that this picture clearly shows is that here you have no maximum principle, right? Because the lower bound of the initial condition doesn't give you a lower bound for the solution. Okay, so this is what two examples for the solution look like. We also implemented some finite difference schemes to do some numerical comparison strictly for that. So, as I said, computationally expensive, but maybe assumed to deliver most reliable results would be a fully implicit scheme. That means we replace the second derivatives by difference quotients, central difference quotients, and evaluate everything, also the nonlinearity at the new time step. Then we have to do a Newton iteration in every time step. The idea would maybe be to use a semi-implicit second order scheme where you evaluate the nonlinearity at the old time step, Then you have only to solve a linear system in every time step. This is much faster. Or you could maybe want to have a higher order resolution, so you could use 5-point stencils that are denoted with this tilde here, and also evaluate this semi-implicitly. And since you want maybe to increase the time resolution in line with the space resolution, you could use, for example, some BDF2 time integrator. Then you end up with this scheme that we also implemented for comparison. Then we studied the numerical convergence. So we fixed the parabolic mesh ratio, so the time step over the space step to the power 4 to be 0.1. And then we let both go to 0. And the rates that we obtain, they agree quite well to what you would expect from the consistency order of the schemes. And also you see that our scheme has a second order convergence, although here the error is higher than with these other schemes. And instead of looking at the densities, would also be natural maybe to look at the problem as particles that are under the influence of this Fisher information. And so for a fixed omega, this curve g of t omega, g is the pseudo-inverse, traces the path of a mass element. So we could plot these paths of test particles, and can take a look how this look like. So in principle, you see here, so this is the space in x, and this is time. Here for the value epsilon 10 to the power minus 1 in the initial condition, and here for power minus 3. And you see here that these particles, these omegas, they are not constant, but they move as the problem evolves. So, and since these omegas are also what we make our grid of, somehow our grid is not constant in time, but it adapts naturally to the evolution of the equation. So you have a sort of natural adaptivity of the grid to the movements of the density. Of course, the equation should also display the Fisher information. So we also computed the Fisher information from these discrete solutions. And we just compared now the most favorable for us or schemes or interesting schemes, this Wasserstein gradient flow scheme and the fully implicit scheme. I'm not sure if it's possible to read from the very back, but you see that for all schemes, and for here we did this also for different number of grid points. For all these schemes, you have a monotonically decreasing Fisher information over time, and you can see that, for example, this Wasserstein gradient flow scheme. So for 50, this is this line. For n equal 200, for n 200 grid points, it is this line. While the fully implicit scheme seems to come from above, right? So of course, all have to approach some of the true behavior of the equation, but you have somehow both schemes. One gives you a lower bound, the other an upper bound for the true behavior of the Fisher information. And what about the time stepping? If you use these semi-implicit schemes, then you have very strong restrictions on the time stepping due to some stability restrictions on this parabolic mesh ratio. And since we have a fourth order equation with the power 4 and h, this is of course very strong restrictions, and this renders these methods unusable in principle in this case. Whereas for our new scheme and the fully implicit, you obtain stable solutions for all values of the parabolic mesh ratio. And also, it's interesting to look at the results in detail. You see here the error of the numerical solution compared to some reference solution on a very, very fine grid. And we computed these numerical solutions for different choices of the time step. So we always solve the same problem, but using different time steps, so larger and larger time steps. And you see, okay, you obtain useful approximations for all choices of the time step. Because I mean, you should not choose a much larger time step than 10 to the power minus 6, because the whole problem acts on a very short time scale. So if you are working here, then you're only doing 3 or 4 steps, right? And what you see here is that for the fully implicit scheme, the error goes slightly up as you take larger steps, which is natural. Here for our scheme, it's a little bit odd that somehow the error does not seem to really depend on this time step. But for us, our interpretation is that the error of our scheme at this moment, how it is largely dominated by the spatial resolution. And because we have to do some reconstruction from the Lagrangian coordinates back to the original coordinates, we introduce obviously also some error there. But on the other hand, the positive message is that we obtain useful solutions for all time steps, so we have no stability restriction on the choice of the time step. So we consider this to be unconditionally stable. Now, and I'm already in my summary, so I've presented you a new second order numerical scheme for this nonlinear fourth order equation that respects its Wasserstein gradient flow structure and this dissipates the Fisher information as fast as possible, so like the original equation does it. In this scheme we have built in mass conservation and non-negativity of the solution, and I've shown you that we have a time-dependent grid, so we have an adaptive grid that moves along with the density, and as we have seen last, there's no restriction on the time step size. Indeed, these numerical results suggest that the scheme is unconditionally stable, which is maybe not extremely surprising because you derived it from a fully implicit. This minimizing movement scheme is an implicit formulation, so you keep that property. Yeah, you could, of course, we focus now in our paper on this DLSS equation, but you could, of course, adapt that to wider class of Wasserstein gradient flows when you replace the Fisher information by other potentials. You could also try to do that for second order diffusion equations, or we could also maybe use potentials containing two or more derivatives of U, which would correspond to evolution equations of 6th or higher order. And of course, it would also be very interesting to do that in higher space dimensions. But since we rely on this pseudo-inverse function here, it's somehow a much bigger step to do that, and we are thinking about how we can go in this direction. But this is for sure left for future work. Yeah, thank you for your attention, and I'm happy for questions.
Any comments, remarks, questions? The lady first.
So your scheme is the what order? Second?
Second order.
Second. So when you do reconstruction from Lagrangian to Eulerian all the time, so you also need to use the second order reconstruction. If you use it just head function, it will give you the first order.
But take a look. We are working on the derivative, right? We're not working on the capital G, but we are working on the small g. Yeah, okay. Maybe you can also see this is a small g, which is the derivative of large g.
So you do the first
so that makes somehow it's
So
consistent.
and if you move to the higher dimensions, you obviously will need to do this some kind of how you do reconstruction moving. So Voronoi, or what would you do to reconstruct from Lagrangian to Eulerian?
Yeah, I mean, first you have to think about clearly how you come up with a good way to compute the Wasserstein distance without the pseudo-inverse. This is maybe the main problem now. That's, I think, not so clear.
First, just an observation about one of the last points you said in your summary. You said generalizing doing it for second order diffusions, but this was already done. No?
Yeah, okay. You could. But there, I think it's also the other way around, right? That it's first optimized, and I mean, of course, it would not be. So I mean, that's why we didn't do it, of course. But we know of this paper, of course. But our approach is a little bit in this way different, that we discretize first and then optimize. But
something more.
You're right.
You said also that you were doing it for the periodic case.
Yeah.
But why? What's the problem to do it numerically with this scheme for the Cauchy problem? There's no problem.
No. But I think as the periodic case is also analytically very well understood, I think we just started with that. So this was like a, yeah.
But the paper of Toscani, Sabarea, and Janazza also tells you that that the problem is well posed, the chip problem.
Yeah, you could also use more.
Not even that, you have even an explicit solution that you could check if your scheme works well, because you have a self-similar solution, which is explicit.
Mm-hmm.
It's like the Gaussian, the heat kernel with
there you
a
could
different exponent in
But
time.
I think numerically it's the same, basically.
Yeah, but that's why I'm saying is there is no big difference.
Yeah, you could also do it for others. Yeah. Mm-hmm.
And concerning the higher dimensions,
Mm-hmm.
I mean, as you know, in that paper with Moll, we wrote that problem in a different way,
Mm-hmm.
which also allows you to somehow find the Wasserstein distance minimizing something, but I mean that you can deal with, and then you had to work over diffeomorphisms
Mm-hmm.
instead of just the pseudo inverse distribution.
Basically what you do is solve Monge-Ampere equations?
Well, no. The diffeomorphism doesn't solve a Monge-Ampere equation. It's the solution of your minimizing problem.
Okay.
So the thing is, instead of approximating just one function, you have to now do a minimize. Well, you have to restrict your minimization to a set of interpolating diffeomorphism or whatever, and then it becomes messy. But certainly, it's.
Here, I mean, with our approach, somehow you end up with a very, very simple problem at the end, because you can evaluate these integrals explicitly, so then it's very. So this was somehow the funny point about it, that it's very simple in the end.
But I mean, you could do linear interpolation 2D too.
Okay.
See what I mean?
Well, you could really solve Monge-Ampere.
Oh, no. Listen, no. I'm not talking about the optima. It's not the minima. It's a different thing.
I'm not talking about the optimal.
I'm not talking about finding the Wasserstein, minimizing the functional, which is Wasserstein plus.
Okay. So
So this is what you had to do. Okay?
develop Lagrange equations.
You don't find the Wasserstein distance between two densities. That's costly and very difficult numerically.
Okay. If no more questions, thank you, Bertram.
Thank you.